Who's your favorite mathematician? Now, if I asked a random crowd, I don't think I'd get too many answers, but this is not a random crowd. So we got John Conway, John Knuth, Richard Guy, Coach Good, James Tanton, Gauss. And we've got a lot of living people. That's cool. Riemann, definitely one of the greats. My grandma and grandpa, I love that. Pythagoras. Sophie Germain, that's right, not all. Gattegno, Caleb Gattegno, fantastic guy. Yeah, and Eugenia Cheng, I'm really a fan of hers. She's written some fantastic books, including How to Bake Pie. Well, we got a lot of answers to that. So I'll show you a picture of my favorite mathematician. He is one of the guys mentioned. If you visited his office, he never knew where anything was, but he had lots of fun models. So here's my version of his name. But it says John Conway. It's spelled out in the Game of Life, which you'll be seeing in a moment. So Conway did many things, but he was especially interested in games and puzzles. He wrote a series of books with Ellen Burlekamp and Richard Guy. I noticed somebody mentioned Richard Guy also as their favorite mathematician, about analyzing games, the obvious ones like chess and Go, but also a lot of peculiar ones like Hackenbush and the Soma Cube. Now at one point he got a little embarrassed, like, well, am I going to be taken seriously as a mathematician? So, but he really loved this stuff. So he made a vow to himself: thou shalt not stop worrying and feeling guilty, and thou shalt do whatever thou pleasest. I found that really, really inspiring in my own work, because sometimes I wonder if what I'm working on is worthwhile or not. Well, if it's interesting, go for it. That's what I say. Now, John died recently, unfortunately, a couple of weeks ago, but we're celebrating him today by talking about some of his work. And if you Google his name, John Conway, mathematician, you'll find tons of cool articles about him. He was quite a character. So some of you I know have met him. So his biggest hit was a game called The Game of Life. He called it a 0-player game. And you're going to play it today. And you will need the following things. Maybe some of you have it. You'll need some blank paper and a marker. You'll need 12 coins, about 12 coins or checkers, something small and flat. Those are pieces. And you'll also need 12 smaller pieces. You can use beans or markers from a game. I'm using some pawns from a Chinese checker game. So I'll give you a couple minutes to go get those things. Yeah, you can use a Go board. And when, I'll tell you what, I'll show you my screen here. I'll show you what I have. I've got some pennies, and I'm going to use these as my little markers. And once you've got this, some of you have it. I'm giving you time if you don't, but if you do have it, draw a grid, maybe like a checkerboard. It doesn't have to have that many squares. Okay, I'm going to go ahead, and if you don't have your stuff, then you can catch up still. But okay, so take 6 of your markers and put them on your board, and if you can tilt down your laptop. If you have a laptop, you can tilt it down to look at your board, just like I'm doing. And then you can if you go to gallery view, you can see what everybody's doing.
Oh, for your game pieces, can I use Chinese checkered marbles?
Those will tend to roll. So I don't recommend it. Unless you, but if that's what you have, you can try it.
All right. Well, what about 12 Lego pieces? Would that work?
Sure. Yeah, they don't have to be round.
All right.
Thanks for muting and unmuting yourselves. Really appreciate it. Okay, so here's the rules. You start by putting some markers down, some pieces down in squares like that. That's your starting configuration. That's your first generation. The rules of life, there are really only 4 rules. will tell you how to get to the next generation. Now, here's where your marker pieces come in. Some of these pieces will die and new ones will be born. The rules are that a piece, well, first of all, we have to say what a neighbor is. Each of these pieces has 8 neighbors. Those are the squares that are next to it, kind of like if you were moving a king in chess. These would be the neighboring squares. So those are the neighboring squares of this penny. Now, how many neighbors does it have? That is, how many of those squares contain a penny? 1, that's right. And it dies because if you have only one neighbor, or if you have no neighbors at all, you die of loneliness. So we're not going to have it go away yet, but we're going to mark it, say, with a blue coin. Now, there's another rule, which is how many neighbors does this coin have? This coin with the yellow on it. And remember, it includes diagonals as well as, it says 4, that's right. But that has 4 neighbors. All 4 of these are neighbors. If it has 4 or more neighbors, it dies of overcrowding. So that one's going to die too. So there's one more square piece on here that's going to die on the next generation. Can you find it? Well, it's this one. And it's this one because I know it's a little blocked by the piece in front, but it also has 4 neighbors. This one's fine because it only has 3 neighbors. If a piece that has 2 or 3 neighbors stays alive. Now, those are the death rules. Now let's have the birth rules. So birth, a square that has exactly 3 neighbors gives birth on the next move. So, for instance, well, I'll just show you. You can try finding them. There are 2 squares here that will give birth on the next move. This is not one of them. This, let's see, like this one only has 2 neighbors, so that's not going to give birth. But this one has 3 neighbors. It's empty on this generation, but on the next one, it will have a piece, so that one gives birth. And this one, the other one is this one. It's also adjacent to 3 in a row. So the next now we're going to determine the next generation. You start by removing all the guys that died. If you're doing it on paper, you can just draw X's on them and then redraw the whole pattern. It's a little slower, but it also works. And then you replace, and then these 2 give birth, so you can put pennies down here. So that's the next generation. That's the whole game of life. Those are all the rules. I remember it this way. This is a shorter way to say it. 2 or 3 to survive, 2 or 3 neighbors, that is, for a piece to survive, and 3 to be born. An empty square with 3 neighbors will be born on the next generation. That's it. Now I'd like you to try your own, on your own paper. Start from here and see what happens. And I'd like to do it with somebody. If you want to be on camera, and it's okay with your parents, please raise your hand and you can turn on your camera. And Terry, can you choose somebody who's got their hand up?
Yeah, so Aria's got her hand up, so I've put her on spotlight.
Awesome. Okay, Aria, do you have a laptop or do you have a, can you point your screen down?
Yeah, I have a laptop.
Okay, let's look at your screen. Okay, please put 3 pennies in a row.
Yeah.
Or whatever you have. What do you have?
Yes.
You got some quarters. That's awesome. Okay, and what do you have little markers you can put on top of them to keep track of life and death?
I have these, but they're not different and they're small. Will these work?
Yeah, those will work fine. Okay, so the question is, first of all, which ones will die on the next move?
This one and this one.
Okay, put a bean on top of each one. Yeah, they don't have to be different.
Okay, I think they both die.
Yeah. And what about the one in the middle?
Oh, that one dies too. Well, not it. Well, it dies next round.
Well, we'll see, but it doesn't die yet.
Yeah.
Okay.
It,
And
it,
what about empty cells? Are there any cells that will give birth?
no, not yet, because 2 or 3 to survive. That one survives, but not 3. There's only 2 next to it. So
Okay. So there is a cell that will give birth, and it's one that touches all 3 of the quarters. Remember, nothing's died yet.
is it that one?
It's look. You got to find an empty square.
Square that touches all
Oh.
3/4.
An empty. Oh, okay.
Don't put a quarter there yet. Just put a bean there to remember that one's going to be born there. And of course, if that works, there's another one that's going to be born on the next generation.
Yeah, there are more.
Yeah, both of those squares touch all 3 of the quarters. So now remove the ones that died. Pieces that died. Careful not to move the beans. That works great. And now there's 2. Replace those beans with quarters. So that's the next generation.
The same thing happens, right?
Right. So without using any beans, what's going to be the next generation after that?
Those 2 die, and 2 are born right there, and then it repeats over and over again.
Yeah, that's a repeating pattern. This pattern is the simplest repeating pattern. It's called the blinker. So that's a good example. I'll show you one other challenge, Arya. Start like this. What happens in the next generation? See if you can figure it out without using any beans.
Oh, so this one gives a child. These 2 survive.
I guess I wasn't clear about that. Squares that already have a piece in it, they don't give birth to a new one. They just stay there.
Oh,
Empty square.
I know. I think this one and that one give birth. Wait.
Does any of those quarter pieces die?
Oh, over here.
Yeah, that one's going to give birth. And what about the 3 on the board? Any of those die?
No.
That's correct. Okay, show me the next generation.
Okay. Okay. Yeah. And wait.
That's right. No one. Sarah says no one dies and 1 square gives birth. That's right. Now, what's the next generation after this?
Next generation is. Wait. So does it have to be one that's touching all 4 now?
No, it has to touch 3. Exactly 3.
Okay.
Is there an empty square touching all 3?
I see in chat somebody asked, is this game infinite? Absolutely. It's best played on an infinite board and it can go on forever. So yes, it's a 0-player game on an infinite board. And by the way, you can answer each other's questions in chat if you're chatting. What happens on the next turn?
Next one is so this one is only with 2. This one is only with 2. So one can't be born. Like they all are touching 3, but wait, yeah, none to be. There can't be a child.
Right. So this is called the cute name for this is called a still life, and it just stays the same. It doesn't change from now on. There are other patterns that do that too. Okay, thanks, Terry. That's I think you got the rules. By the way, when the game of life was invented, this is exactly how they played. They played on paper. Because they played on computers later, but personal computers didn't exist when this game was invented. But now we got Zoom. And for those, some of you know about the pencil. If you go up to the top of your screen, you can grab a pencil and draw. Now, what I want you to do is draw, like, get a color other than black, get like red or something, and draw an X on the pieces that are going to go away on the next generation. Which pieces die?
How do you get a pencil again?
It's up at the go up to the top of the screen and you'll see a pencil icon. It's called, the word under it is annotate. You can try drawing.
I don't have the pencil icon.
Okay, so we got different people arguing about what some ideas. This one's, everybody thinks this is going to die. If you don't have it, I'm not going to explain it right now. Just watch what's happening, and you can learn it later. See, this one will definitely die because it only touches one other. This one dies because it's going to touch one other. Now I've got some arguments about this one. Is this going to die or not? The one with blue on it. How many does it touch? How many neighbors does it have? It has 2 neighbors. 1, 2. Right. Remember, it has, this one is a neighbor too, because that one hasn't died yet. So it has 3 neighbors. That's right. And what's the rule about it if it has 3 neighbors? Does it live or die? Well, remember, the rule is 2 or 3 to survive. So that one actually survives. It does not die. And I'll show you the next, so only two die. Now draw a dot where there's a square that's going to give birth. Yeah, that's one of them. That one's kind of tricky, but can you see how it has 3 neighbors? 1, 2, 3. Cool. Yeah, beautiful. And down here has 3, just like in the pattern Arya was making when she was making the blinker. Those are the only 2 cells that give birth. So 2 die, 2 give birth. The next state of this whole thing, can somebody erase it? Yeah, please erase the screen. Please stop scribbling on the screen. But thank you. This is the next state, the next generation. It has 5 in it too. In the interest of time, I'm going to move on because I'd like to end by 12:30. And here's the next state. Now this one looks a little suspiciously like the first one. What sort of transformation did it undergo to get from one to the other? Here's the first one. Oops. And here's the third one. For you geometry fans, that's called a glide reflection. It's a flip. Oh, yeah, somebody's writing in there. Obviously, it's a flip and a rotation. Which that's right. Okay, let's go 2 more generations forward. Oops. So here it is. It did another glide reflection, and you'll notice it's the same shape as the original, except it went from here down to here. That's called a glider because it's a pattern that repeats like a blinker, except it moves at the same time. So in case you were wondering if there was a pattern that lived forever, yes, it lives forever. People are chatting about all sorts of things. It's upside down, vertical reflection, back to the beginning. Yes, so this is one of the first really cool things that happens in life. And this I don't know, I find that this game reminds me a lot of Minecraft. It's just, for those of you who've played Minecraft, you know, it's a vast world where you can build kind of anything, and it really sucks up your time. So does this one. Okay, now I'd like you, it's almost 12:30. I'm going to leave you, I'm going to pause for right now, but I want to give you one last thing that you can do all next week. So Terry, can you put the URL in the chat?
Sure.
So this is a version of Life. All of you are probably itching to play it on your computer. So we've got two URLs. The first is a web page that explains the game and gives you a little playground, a sandbox for playing Life. It's a very nice looking one. The second one, the author Tom Rokicki is here. It's called Golly, and this is a very full Life engine that can handle gigantic boards. And it's used by mathematicians to really explore what Life can do. So if you've got, for most of you, I suggest that you go to the first one. You don't have to download or anything. The academo.org demos, Conway's Game of Life. I've got the URL on the screen as well. Go there, and a challenge that I find really fun is try putting 4 dots in a row and then run the game and see what happens. Then try 5 dots in a row, clear the screen, try 5, 6, 7, 8, 9, all the way up to 10 dots in a row. Now it's 12:30, so if you need to go, I just want to leave you with that and have fun exploring. And if you want to stick around, I want to give Tom a chance to talk about his program if you're up for it. And I'll show you some other Life patterns. Tom, would you like to say something about your experience with the Game of Life? And Terry, can you unmute him?
He should be able to unmute himself.
Okay, you can unmute yourself. I don't know if Tom's still here, actually.
He is.
Okay. If you want to go, you can. You don't have to. I know I'm putting you on the spot. Well, anyway, feel free to jump in if you want. Now, so I guess I realized I was going to have everybody explore these patterns. Have people been able to go to the academo.org site? Now, the tricky thing is you'll still hear my voice, but you won't see me if you're going to that site. I guess I want to try this as, yes, there. I want you to go to that site and tell me, and you can write down what happens if you try one of these patterns. And everybody try different ones. You don't have to go in order. Try at least 2 of these patterns and see, does it live, does it die, does it repeat, what happens? I'm going to give you like 3 minutes and then we'll come back and report what you found. Oh, cool. People are writing on the screen. I love it. 7 turns into a still life. Cool. If you want to type on the screen, you go up to the annotate button at the top and you can choose a tool for typing. Or if you don't want to draw on the screen, you can just unmute yourself and tell me what happens to one of these. Bye, Jean. Some people have to go there. Yeah, if you. Five in a row is very interesting, says Sarah. I saved the best for last. I really love 10 in a row and what it does. 5 goes back and forth between 2 patterns. Okay. So that's called an oscillator. So oscillator, and it has two states. Actually, we call it period 2. Period means how long it takes to repeat. 8 goes a long while before settling into a steady state. Does it turn into a still life or an oscillator? Still life. Okay, great. Yeah. Amanda, says she's confused. What's your question, Amanda? You can unmute yourself. Were you? Okay. She says, never mind. Okay. Cannot tap the link. Yes, that might not work on an iPad. I'll be sending out emails afterwards with all the links, and you can try it then also. I'm not on an iPad. You can also try copying the link and type it into a browser, or copy and paste it into a browser. And the link is in your chat. Hannah says 10 goes between 15 patterns. That's right. Okay, so I'm gonna clear the screen here. So there are, you may be wondering some questions. Is it possible? These are some of the questions that came up certainly when I was thinking about this game. One was like, we've already seen that you can make a game that a pattern that repeats or stays the same. One question that might come up is, can you have a pattern that grows forever? What are some other questions? And you can type them in chat, or you can. Sarah has an interesting question. Are these the only rules? What about other rules? Are there other interesting rules? Like, what if it was 4 squares to give birth? How would that, or 2 squares to give birth? What would that happen then? Are all periods possible for oscillators? Good question. Like, is there an oscillator of period 7? What about 3 dimensions? Yeah, good questions. This is the thing that made life so exciting to me. There are a lot of questions, and some of them are hard. Some of these are probably, I don't think anybody knows about all periods, but people have explored oscillators of many periods. You've just seen oscillators of period 2 and 3. Well, I'll show you a couple more, some more types of patterns that do come up. Are there any rules that would create infinite growth for any configuration? That's a good question. I won't answer that one. It's a good question. How could you change the rules so that the thing, any pattern you put down would just grow forever? And Sarah asks also, does it have applications in science and engineering? We'll get to that. So I'm going to show you a few more things about the game of life, and then we'll have question and answer for those who are sticking around. And thanks for staying around. Here's some common still lives, and they're funny names. John Conway really loved to give fun names to things. Wait a minute, we got a question from Hannah. How much longer does this last? I'm going to stop in about 10 minutes. But you're welcome to go whenever. I certainly will understand. Here's some oscillators of different periods. The pulsar has period 3. And you already discovered the period 15 one, which is got the fun name of the pentadecathlon. Penta means 5 and deca means 10. So that's a period, the prefix for 15. You saw the glider. Here are spaceships in general of different sizes, and there are much larger ones. There are even puffer trains that are like spaceships, but they leave stuff behind. Now here's one of my favorite patterns. This answers the question, is there a pattern that grows forever? This one does. What do you think this one's called? Type your answer in. Or okay, bye, Sarah. I'll be sending a follow-up email with all these links and the slideshow. This one, Conway didn't know if there was a pattern that grew forever, so he put a $50 Carl says an Uber machine. Hannah says a bow and arrow. Skona says a shooter. Yeah, it's a pattern that repeats, but it generates gliders. Terry this morning said it looked like a mining, it was mining stuff from the blocks at the end.
This is, yep.
This was invented by a group at MIT working together, including a fellow named Bill Gosper. It's called the glider gun. It was the first infinitely growing pattern. Now I'm going to skip to a much crazier pattern. And that is, let's go, here it is, just much bigger. On the right, it's got a whole bunch of puffer trains that are leaving behind patterns. And some of those puffer trains are shooting out gliders. And those streams of gliders collide to create, of all things, a glider gun. And each glider gun is then sending out gliders. And for those mathematicians in the audience, this answers the question of can a pattern, you saw a pattern that grows linearly. This one grows as as the generation squared. Here's some other patterns. And these patterns you'll all find in the game called Golly, which you can download. And we've put the link in the chat. This is a small computer that has been built inside of the game of life. So that's kind of fun. This is a computer built in life, built on a computer. And it's using gliders to communicate as streams of information to communicate from one place in the computer to another. Yes, these are truly stupendous. Now, Sarah asked earlier about applications. Yes, well, life is an example of, these types of machines are called cellular automata. Cellular means, well, it's just made up of a bunch of cells, or in this case, squares. Life only has 2 states for each cell, but you can have more. So cellular automata in general, the first one had 29 states and was invented by John von Neumann. And automaton means like a robot or a machine, something that works automatically. It was invented by this fellow, John von Neumann, who was one of the first people who invented the electronic computer. This is the ENIAC from the mid-1940s. It was invented during World War II. Those of you who've seen the movie, The Imitation Game, about Alan Turing, know that he was in the same generation of scientists. Turing was in England. Can a machine build a copy of itself is a question that John really wanted to know. And he had a colleague named Stanislaw Ulam, who was already studying cellular automata, but to study how crystals grow. Because crystals grow very much like cellular automata. Atoms are a lot like cells, and they have rules for how things can grow next to them that are very geometric. And the two work together to create the first cellular automaton. So here's some pictures of other cellular automata. And yes, the practical application is they can be used to model different physical phenomena. They can have more colors. They can, some of them imitate biological growth. here's a three-dimensional cellular automaton. And here's a cellular automaton that John von Neumann designed to answer his question about whether an automaton could reproduce itself. The answer is yes. And it's this is a machine that creates a copy of itself. And the machine itself has a copy of itself that it looks at and imitates. And that's really central to computers. Of course, it's central to life. You know, we have DNA, and that allows us to build copies of ourselves. Finally, if you want to get wowed by all these crazy things, there's a wonderful movie. If you look up The Game of Life on YouTube, you'll find this epic movie, which Terry has typed it into the chat. Please wait till after the presentation's done to watch this, but you can, here's the YouTube link. And it's really nuts what people have done. Okay, please unmute people, and if you have any questions, you can unmute yourself. Any questions? Or Tom, if you want to talk about Golly or the Game of Life, you're welcome to.
Well, I mean, I've been playing with the Game of Life for 40 years or something like that since I was introduced to it at an age pretty much similar to the participants here. And I've had a lot of fun, first with checkerboards and go boards and pieces like Scott showed originally, to programming it on bigger and better computers and everything. And it's just, I mean, it's amazing what you can engineer and everything. So it's always been a source of entertainment and joy for me. And Golly is just the program that a friend and I wrote pretty much to share that with other people. So, but Golly is sort of like a chainsaw. It's good for big patterns and stuff like that. The little applet that Scott linked to is better for just, you know, playing around maybe and get started. But it's a lot of fun. You can waste a lot of time on this.
Do you have John von Neumann's rules in there?
There sure are.
Ah, awesome.
As well as, you know, hundreds of other rules and stuff like that. It's amazing. And the pattern catalog is amazing. I mean, you can walk through the pattern catalog and read the description using info to look at the comments and see what they do, and you'll see patterns that generate prime numbers and calculate pi and all sorts of other things. And they're all doing it using the very simple rules that Scott described. There are 2 neighbors or 3 neighbors, stay alive, and 3 neighbors and that's it. So simple rules can do literally anything computable, and that is just mind-blowing.
Awesome. Thank you so much, Tom. You mentioned we had an online tribute to John Conway, I guess a week ago, and Tom was there. He also mentioned that programming the Game of Life taught you a great deal about programming.
It sure did. And for any of you all who are playing with programming, I really encourage you to try your hand at trying to write the Game of Life. It's pretty simple, but then you run into all sorts of interesting challenges as you try and make it bigger and faster. And for me, that's driven a lot of what I know about computer science. So it's a lot of fun. I mean, the things you see on the screen have just endless novelty, always new things happening, and it's very entertaining.
Thank you so much, Tom. Yeah, to make a screen like this work, I've seen Life programmed in like the Scratch from MIT, but that probably wouldn't be able to support. It would clog. It wouldn't support this pattern. It's far too big.
And it is so amazing that so much was done before we had computers that were able to do this stuff. Just
right, definitely. We start off with John Conway, so I'll end with one last comment. John himself, if you look up John Conway, Game of Life, you'll find out that John was not too thrilled by the Game of Life, which seems really odd. Well, that's inaccurate. The Game of Life, he's perfectly proud of it. He just doesn't. He considers it a fairly minor creation, and he found it kind of irritating that everybody said, "Oh, John, you're the creator of the Game of Life." But he kept thinking, "Well, there's all these other cool things that I created."
I think a lot of that has to do with effort. He put a great deal of effort into a lot of his deeper mathematical work, like the classification of groups and stuff. And that effort isn't necessarily acknowledged by the recognition you get for things. You know, you do something in an afternoon and you put it out there and you get famous for it, but then you spend 12 years on your PhD or whatnot, or your research, and you figure out some big fancy thing, and the amount of recognition and response you get is not commensurate with the effort. That's a challenge for a lot of people. But John definitely liked the Game of Life. It just wasn't the thing he wanted to talk about all the time, and that's what happened. People came up to him and said, "Oh yeah, Game of Life," and he just got tired of it after a while, I think. So
if you enjoy the Game of Life, in that spirit, I really encourage you to explore some of the other things that John created. My favorite is other of his creations is called Surreal Numbers. And it's a magnificent creation. He was very proud of Surreal Numbers. Okay, well, thank you, everybody. Here's my email address if you have questions or want to follow up. Scott@scottkim.com. Thank you, everybody. I see people are logging off, and I'll see you next Monday. If you want to tell your friends about it, they can sign up at mathmonday.net. We do this every Monday at noon Pacific time. And thanks for coming. Yep. Thanks, Aria, for being on camera. Thanks, Sally. I'm really happy to have a chance to share this game. I was blown away by it when I saw it in 1970, just like everybody else was. And it was published first in Scientific American and by Cloud and Cloud McCloudy. You said you program in Scratch, so try building a version in Scratch. Okay, so now we're into overtime. If you want to stay, you can, but we're saying goodbye right now. Jennifer Kane asks, can you explain a bit more about surreal numbers? Sure. Well, first of all, there's a book about surreal numbers. I think it's just called Surreal Numbers by Donald Knuth. That's kind of looks like a children's book story, though it's pretty sophisticated. Surreal numbers include all, there's integers, the counting numbers, integers, fractions. Then there's the real numbers, like square root of 2 and pi. Those are some of the types of numbers that are familiar to most of us. The surreal numbers go on to include different varieties of infinity in that scheme. Some of you may know that Georg Cantor explored different types of infinity. There's not just one type. Surreal numbers include things like the reciprocal of infinity, 1 over infinity, which you might think, oh, that's just 0, which in some versions, yes. But in the surreal numbers, he distinguishes 1 over omega and 1 over omega plus 1. Those are all numbers too. They all kind of look in the square root of infinity, crazy stuff like that, yeah. The cool and what was amazing is all the numbers I just described, real numbers and transcendental numbers and irrational numbers. If you write out the axioms to create all those, it's a very long, complicated thing. So, Conway was just trying to understand how to play the game of Go, and he accidentally created a new way of thinking about numbers. And it only has two rules at the beginning, 2 axioms, and it generates all the numbers. So it was profoundly simple and profoundly richer. And as he described in his biography, he went around in a daze for like weeks thinking, I've discovered something that nobody's seen before. And it was truly one of the best experiences of his life, I think. That's a little bit about surreal numbers.
Scott, do you want to mention the relationship between surreal numbers and games?
If you have a way of explaining it, sure. I know they're related, but it's a little, I'm not quite sure how to put it into words.
So the interesting thing, the thing he started surreal numbers with really was in games, combinatorial game theory. And he showed that a lot of very interesting games were exactly equivalent to specific surreal numbers. Specific positions were equivalent to specific surreal numbers. So this set of surreal numbers actually forms the basis of a lot of game theory. And you can do a lot of interesting things in games using it. So it's absolutely fantastic.
That's right. And his books, Winning Ways and On Numbers and Games, spell this out in great detail. Right. Each surreal number is associated with the state of a game. The easy thing is to say, well, the first player wins and that player loses, so that might be a 1. Or in the other way, it might be a -1, something like that. But there are some states, but you can talk about like adding 2 games, like in Go, near the end of a Go game, it really breaks down into, there's a pocket of activity here and a pocket of activity here. That's a lot like adding 2 games. And he made that formal with surreal numbers. You can add 2 surreal numbers and it's adding the 2 games, which is to say you can make a move here or a move here. Well, thank you so much for giving me a chance to share this. This is stuff I love, and I was very excited to give everybody a chance to see it. I hope you enjoy it. Have a good week, stay safe, and I'll see everybody next Monday. Take care.
Take care.